Welcome to the course Power System Operation and Control. Lecture number 10, Steady State Frequency Deviation Analysis with Controller. In the previous lecture, we have discussed about the concept of control area, and then we have discussed about load frequency control and economic dispatch control by using Central Economic Dispatch Controllers, CEDs. And we have discussed about tie line power and what is the necessity of having interconnected power system. And then we have developed composed block diagram for two area load frequency control. And then we have modeled for two area load frequency control by discussing various equations. In this lecture, we'll discuss about the frequency deviation and its impact on two areas. So frequency is a very important parameter that will indicate the real-time balance between power generation and load demand. So usually we have to maintain the total power generation should be equal to total power demand. This is the ideal case. But practically what will happen in the real scenario, continuously there will be changes in the load demand. So whenever there is a change in the load, the PD value will change. Then accordingly, we have to change the PG value also. Suppose if we are not changing this generation in accordance to power demand, then we can see the variations in the speed, which will show its impact on frequency. Then frequency may not be equal to the nominal value, that is 50 Hz in Indian grid system. So any disturbance in generation or load causes deviation from this nominal frequency value. So in the interconnected system, disturbances in one control area may show its impact in another area also. So load frequency control is implemented to maintain this system frequency and scheduled tie line power flow. So we have to maintain both frequency and also the scheduled tie line power flow. By making delta theta is equal to 0, we can achieve whatever the agreed power is there between the two areas that has to be flow through between two areas through transmission line, that is called as tie line. So the frequency stability is very much essential to have secure, reliable and economic operation of power grid. So the frequency deviation basically refers to the changes in the system operating frequency from its nominal value. So it may be either above the 50 Hz or below the 50 Hz. In both the ways, we may have frequency deviation, and this frequency deviation is the resultant of imbalance between generator power and load demand. Suppose when the load demand is greater than generation, then frequency will decrease. That means if PD is greater than PG, then frequency will drop from this 50 Hz value. And if the generation is greater than power demand, then frequency will increase from this 50 Hz nominal value. So here the frequency is very much directly related to the rotor speed of synchronous generator. So let's say the synchronous generator speed is ns, because we know that synchronous generator always runs at synchronous speed, that is given as 120 F by P. That speed is given as 120 F by P. So here you can see there is a strong correlation between this speed as well as frequency. So even small deviations of frequency will affect power quality, equipment performance and protection coordination also. Because most of the load's performance depends on whether we are able to give constant frequency supply to the loads or not. Because all our loads are designed to operate at nominal frequency. If the supply, whatever we are providing, is not having that nominal frequency, then obviously it will show its impact on the load's behavior. So continuous frequency deviation may lead to system instability and possible blackout also may occur. So continuously it is not advisable to have variations in the frequency value. So what are the different causes for frequency deviation? There are so many reasons because of which the frequency is deviating from the nominal value 50 Hz. The first reason is the sudden increase or decrease in the consumer load. Because consumer is not giving any kind of information, prior information to the power system operators that I'm going to increase the load or decrease the load. So that is one of the reason why frequency may try to deviate from the 50 Hz. Generator tripping due to faults or maintenance issues. So all of a sudden, let's say there is a fault. So generator may trip, then it will show its impact on PG value. Then there exists some unbalance between PG and PD. That will also one of the reason for causes for frequency deviation. So all of a sudden, the transmission line may outage because of some altering power flow patterns. And then variability and intermittency of renewable energy sources like wind and solar. We know very well that the wind and solar is very much intermittent in nature. So whenever the input energy for these wind and solar power plants changes because of wind velocity and solar light intensity, the output also will change. So that will show its effect on PG value. And poor load forecasting and scheduling errors. Let's say we have forecasted properly, then there is no issue, we can plan generation accordingly. But suppose if the forecasting itself is having some error, then we cannot plan good number of generating plants to meet the required load demand in the future. Then definitely we will have some kind of unbalance between the generation and power demand. Short circuits and disturbances may also cause some temporary imbalance. Failure of control mechanisms such as governor failure or automatic generation control AGC failures may also result into frequency deviations from its nominal value. So these are the only few reasons, but likewise, if you observe the entire power system, we also have so many other reasons because of which the frequency may deviate from the nominal value. So what is a two-area interconnected power system and how our frequency deviation will show its impact? We'll see that now. So a two-area power system consists of two geographically separated control areas connected through a transmission line that is called tie line, what we have seen in the previous lectures also. So each control area contains multiple number of generating units, various number of loads and turbine governor control systems. So under normal conditions, both areas operate at same frequency and scheduled tie line power exchange. But under the abnormal conditions, the frequency may deviate and the scheduled tie line power may not be exchanged between the two areas. So interconnection allows sharing of spinning reserve, improved system stability, better utilization of generation resources, and economic power transfer exchange between the regions which are connected through a transmission line or tie line. So now let's see the impact of frequency deviation in area 1. Suppose let's say there is an increment in the load in area 1 that will result into frequency reduction because of deficit of generation. So generators in area 1 slow down because the load has been increased. So because of which there will be a reduction in the rotor speed and also electrical frequency. So now the tie line transfers power from area 2 to area 1 because of increased demand in the area 1. So now the voltage profile in area 1 may deteriorate due to increased reactive power demand. So persistence deviation may trigger under frequency load shedding schemes. So mechanical and thermal stresses on generators may increase, reducing equipment life. Suppose let's say if we are not maintaining this tie line, then all these consequences may occur in area 1. So similarly in area 2, what will happen at the same time? The area 2 is supplying some additional power through tie line support mechanism because of increased power demand in area 1. So generators will increase output leading to higher fuel consumption and reduced reserve margin in area 2. Then frequency in area 2 may decrease slightly due to interconnected operation because now area 2 is supplying power to area 1. So because of which the area 2 may feel like it's overburdened. Then because of that the frequency may fall down. So overloading of transmission lines and generating units may occur. Continuous disturbances can cause inter-area oscillations and reduced synchronizing power. So whenever the synchronizing power value goes down, then the stability issues may arise. So economic operation is now disturbed due to unscheduled power exchanges. So because of sudden unexpected load increment in area 1, all these are the consequences that occur in area 2 as well. So now, as a whole, what is the impact of this frequency deviation on tie line and overall system performance? So tie line power flow changes in response to frequency deviation between the two areas. So power flows from always high frequency to low frequency region, because high frequency region will have surplus power generation and the low frequency region will have deficit generation. So large deviations may cause tie line congestion and oscillations. Protection relay mall operation. So whenever this overburden occurs, the frequency is deviating. So because of frequency changes, some of the relays may operate mall or may function mall. That means the relay does not want to operate, but because of changes in the frequency, it may operate. That is called mall operation. So reduced system damping and stability margin. So as I mentioned, the stability issues may arise. So overall system impacts include poor power quality and voltage fluctuations, overheating and reduced life of relating machines, risk of cascading failures and large scale blackouts. So our load frequency control LFC has to ensure restoration of frequency and scheduled power interchanges. So obviously, all the consequences may try to arise in the real power system because of continuous changes in the load demand. But our frequency controllers has to take care and bring back to the variable frequency to the nominal value. And also it will try to maintain the scheduled power between the two areas. So this is the composite block diagram what we have developed in the previous lecture for a two area load frequency control. So let's consider this block diagram again for the case of analysis in this lecture as well. So we have seen that whenever there is a sudden change in the load, there exists some frequency deviation. So that steady state frequency deviation, how it will show its impact if we are going to implement some controller. So let's say there are some step changes in both the load demands in area 1 and area 2, that is delta PD1 and delta PD2 will occur simultaneously in both areas 1 and 2. Then because of our output signals of all integrated blocks and they become constant, in order to bring the input signals to 0, we should have or we should maintain the following set of conditions. The first condition is delta P I1 plus B1 into delta F1 should be equal to 0. This is nothing but ACE1 of area 1, area control error of area 1, and the second equation represents ACE2. This is the area control error signal of ACE2. So if you want to have zero steady state frequency error, the ACE1 and ACE2 both should be equal to 0. So this is possible whenever you have difference between two frequency deviations is equal to 0. That is delta F1 and delta F2 difference will become equal to 0. And now let's consider the tie line power expressions which we have derived in the previous lectures, delta P tie 1 and delta P tie 2. Once again here. So we can take the ratio between these two delta P ties. Delta P tie 1 by delta P tie 2 is equal to minus T12 by minus T21, and that is constant. So now the previous equations and up to this equation, all these are simultaneously satisfied only when delta P tie 1 is equal to delta P tie 2, and that should be equal to 0, and at the same time delta F1 is equal to delta F2 and that is equal to 0. So under steady state condition, so the change in the tie line power and frequency of each area should be equal to 0. So this can be made possible only by integrating ACEs in the feedback loops of each area. Suppose if there is no concept of ACE, we cannot achieve all these conditions. We cannot maintain the steady state frequency error as 0. That is an important observation by having all these conditions and the previous equations. So now let's see, by taking some of the example values for all the gains and time constants, how the response will change. Here you can see the first graph shows change in tie line power due to step change in load. And the second graph shows change in frequency of area 1 due to change in area, the load in area 1 also. Now here you can see with integral action, this is the curve, how it is maintaining. Always we are able to have some discrepancy in the tie line power. But in the optimal case, we can, by using some controller, we can reduce to up to certain extent. Similarly, when you think about frequency, if we are going to implement integral action, even though we are able to have 0 steady state frequency, still it is going to make some kind of oscillations. So we have to tune our integral gains properly so that it will not make any kind of oscillations and it will try to maintain the constant error, which is almost close to 0. So all these are possible only by incorporating ACE signals. So now let's discuss more about what is this ACE. So ACE is nothing but area controlled error. So this is a very key concept in power system operation, especially in the multi-area interconnected power systems. So basically this ACE represent mismatch between the actual and scheduled values of tie line power and power system frequency. So the ACE can be expressed as delta P tie plus B into delta F, where delta P tie is called change in tie line power. That means actual value minus scheduled value. Delta F is called frequency deviation and B is called frequency bias constant expressed as megawatt per H. Suppose if ACE value is equal to 0, then we can conclude that the system is perfectly balanced. That means there is no error in tie line power and frequency. Suppose if ACE is not equal to 0, there is imbalance in power exchange as well as frequency. Positive ACE value will represent excess generation or export. We have to export the power from one area to another area. And negative ACE will represent deficit generation or import power. We have to import power from other area to our area. So what are the different components of ACE? As we see in the equation, ACE is expressed as delta P tie plus B into delta F. The two important components of this ACE signal are, one is delta PTI and another one is delta F. So here delta P tie represents deviation from scheduled inter-area power transfer, whereas delta F indicates overall system imbalance, and the other component is constant B, which will represent how strongly the area responds to frequency deviations. So now let's try to go a little deep with respect to ACE. In an interconnected system, each control area is responsible for maintaining its own load generation balance, scheduled power exchange with other areas. So whenever there exists some sort of disturbance because of load change or generation loss, the frequency may deviate and the tie line power may also change unintentionally. So now this ACE has to measure this imbalance, whatever are happening because of load change or generation loss, and it has to act as a control signal in AGC, where AGC is called or expanded as automatic generation control. So now we can have the significance of ACE. It is going to maintain the system frequency constant equal to nominal value. It is going to control the tie line power flow, And the AC signal will ensure proper load sharing between the two areas, and it will ensure proper power balance between the two areas. That means it will maintain total power generation should be equal to total power demand plus losses. And it will try to ensure to maintain system stability, and it will enable automatic action by using AGC, automatic generation control, and it will support multi-area coordination. Suppose let's say if ACE concept is not incorporated in multi-area, then all the objectives are not possible. So the advantages of using ACE is we can accurate monitoring system condition, we can do fast corrective action, we can increase the reliability, we can have efficient power sharing. For example, if load increases in one area, frequency will decrease, then tie line will import or increase power, then AC will become negative, then AGC increases generation so that the balance will be restored in the power system. So we can conclude that our area control error is playing very much important role, and it's our main objective should be we have to make ACE should be equal to 0. So now let's see what is load frequency control with AGC. So load frequency control is a mechanism used in power system. As we have seen in the previous lectures, it is used to maintain the system frequency and tie line power within the acceptable limits in spite of load variations. When we are going to combine this LFC with AGC, it becomes fully automated system for real-time control to provide some of the objectives like to maintain the system frequency constant and to maintain the scheduled tie line power exchange and to maintain proper load sharing among generators. So what is the need for having AGC together with LFC? In the practical power system, the load will keep on changing continuously. So manual control is very slow and inaccurate, and of course it is not efficient one. So any imbalance in the real time will cause frequency deviation and power flow disturbances. So this AGC is going to provide automatic adjustment of generation based on the system deviations. Suppose if we are unable to maintain this AGC with LFC, we cannot achieve automatic operation. So the role of AGC is to provide system frequency constant and tie line power to the scheduled values. And you can summarize that AGC is just an extension of LFC that is going to eliminate steady state error in terms of frequency. So let's try to understand graphically what is this LFC with AGC. Here you can see there is a continuous load change, and here we can observe the speed governor is controlling the input of turbine, and turbine is coupled to the generator, and generator is giving power to our transmission and distribution network. So continuously there is a power exchange between two areas in the form of tie line. So we are going to monitor the load changes continuously. Accordingly, we are going to calculate ACE signal, and that will be given as an input for the AGC. So AGC controller will generate some sort of output signal, and that output signal will be given to generator controller, which is going to restore the frequency, and at the same time which is going to maintain tie line power balance also. So after a certain time, after implementing this LFC with AGC, definitely our frequency deviation is going to decrease and it will become to 0 after a certain time. So this can be made possible only by making this kind of automatic action with respect to AGC and LFC. So what are the components in this LFC with AGC? We have speed governor, we have turbine, and we have a generator, we have load, and we have AGC controller, so which is going to receive ACE signal and sends corrective signals to the generators, as we have seen in the previous diagram. And how it is going to work? Let's take one case and example. Let's say the load is increasing. When the load increases, the frequency will drop due to less generation than demand. Then governor will come into action. That is what primary control. It will increase the turbine input so that the further frequency drop is going to stop. Then secondary control will come into picture. That is nothing but our AGC. It is going to calculate ACE signal and it will adjust the generated output accordingly. Then the system will be restored to the previous conditions. That is, frequency will come back to nominal value, Thailand power will be equal to scheduled value, and ACE value will become equal to 0. So what kind of levels we are implementing here in the AGC? Two levels we are implementing, as we have seen in the previous lectures also. One is primary control, that is called governor control, and another one is secondary control, AGC. Here the similarities and differences are mentioned here. The primary control acts immediately and it responds to frequency changes very quickly, and it stabilizes the system also very quickly, but it cannot restore the exact frequency. That means it cannot bring frequency exactly equal to 50 Hz. So to overcome this drawback, now we are going to implement secondary control. So this secondary control will come into picture after primary control. So once the primary control does its job, then secondary control will come into picture and it will take the help of ACE and it will try to bring the frequency to 50 Hz and also maintain the Thailand power to the scheduled value. So now one more control is also there, that is called tertiary control. So this is a kind of manual control or economic dispatch. Optimizes generation cost. As we have seen in the previous classes, whenever there are multiple number of generators, let's say PG1, PG2 and so on up to PGN, the total power generation is given as sum of individual powers. So this sum of individual powers should be equal to our total power demand, provided the total cost of generation CT should be minimum. So this can be taken care by incorporating the other control, that is called tertiary control. So now what is the advantages of having LFC with AGC? One, we can achieve improved frequency control to bring the actual frequency exactly equal to nominal frequency, that is equal to 50 or 60 Hz, and to have accurate Thailand control to maintain the scheduled power exchange between the two areas, and to have better stability, because when we have better stability, the oscillations can be reduced and the disturbances also may not show its impact on the system. And to have automation, reduces need for manual intervention. So as a human being, we no need to observe the frequency or load demand or power generation manually. The system itself will take care of automatic corrective actions because of closed loop operations. And we can have efficient operation so that our resources can be used optimally, so that we can reduce the total cost of generation also. So as a whole, we can conclude that LFC along with AGC plays a vital role in achieving all these objectives. So in today's lecture, we have seen how the frequency deviation will occur and what is its impact on a two-area power system. We have seen, and we have seen what is the impact of on Thailand and the overall system performance. We have taken a case study as an example. Suppose if the load is increasing, then how the system will show its corrective actions in the sequential manner we have seen. And we have seen about area control error, which has two important components, that is delta P tie plus B into delta F. So the area control signal will take care of bringing this delta F value equal to 0 and delta P tie value also equal to 0 by using PI controller as well. That we have seen. And we have seen the importance of ACE, the significance of area control error. And then we have seen by taking some assumed values for time constants and the gain values, we have seen the graph, how it is going to change its output. And we have studied about the steady state frequency deviation. And then we have studied about the load frequency control along with AGC. What is the objective of having this and what is the necessity of incorporating this AGC and LFC? and what are the benefits we are going to achieve when we use this AGC along with LFC control. So this completes the discussion about the frequency deviation and its impact on two-area system along with LFC and AGC. Thank you all. We'll meet in next lecture.